So, hello and welcome to lesson 11 in our study of optimization 2. So, in this lesson, we will talk about transportation problem solution methods. So, when you have a transportation problem, what are the methods we can use to solve it? So, I'm Boydo Kandrino, a final year student of mathematics KNUST, and I'll be taking you through this lesson. So, transportation models are solved manually with a tableau, as in the simplex method. And transportation models do not start at the origin, where all decision variables equal 0. They must be given an initial feasible solution from the initial simplex tableau. Hence, solving a transportation problem using a simplex tableau can be done in two phases. Okay, so when you have a transportation problem and you are solving it, it can be done in two phases. So in the first phase or stage, we find an initial basic feasible solution. And in the second phase or stage, we build on the solution from the stage 1 to make sure that we get an optimum solution. Okay. So that's what we do when we are solving a transportation problem. The first phase, we get an initial basic feasible solution, and after that we build upon that to get an optimal solution, right? So let's look at methods of obtaining an optimal basic feasible solution, right? So with the basic feasible solution we're talking about, how can we get that? So there are several methods for doing that, but we shall study the following since they are the most commonly used ones, right? So we will study the northwest corner method, the minimum cell cost method or least cost method, and the Vogel's approximation method, VAM. Okay, so those are the methods for deriving or obtaining the initial basic feasible solution. Now, what are also the methods for checking optimality? So that one too, we have two of them that we will study: the stepping stone method and the modified distribution method. So with the rest of the things we'll be doing in this video, we'll be talking about the methods for locating an optimal basic feasible solution. We talk about all the three: the northwest corner method, the least cost method, and the VAM method. Okay. Then in the next video we'll talk about stepping stone method. In the next one we'll talk about the modified distribution method. Okay. So methods for locating an optimal basic feasible solution. So note that when you are given a transportation problem to solve, the first thing that you have to do is to locate your basic feasible solution. Okay, there shouldn't even be optimal here. So basic feasible solution. So let's just consider the tableau below for the transportation problem, right? So this is a tableau we have for a transportation problem. So we got this from the problem that we looked at in lesson 10 when we started with the introduction to the transportation problem. Okay, so this is what a tableau means. It means we have three sources: source 1, source 2, source 3, and we have three destinations: destination 1, destination 2, destination 3. And we want to transport goods from source 1, source 2, source 3 to these destinations. Okay, so transporting a unit of the good from source 1 to source A has a cost of $6. From source 1 to source B has a cost of $8, and so in the table, right? And there is the supply from source 1. So the supply from source 1 is limited to 150. That of source 2 is limited to 175, and that of source 3 to 275. And the demand from source A is limited to 200. That of source B is limited to 100. And that of source C is limited to 300. And you could see that demand and supply are all 600. So we have a balanced transportation problem, right? And we are going to solve that. So let's look at the first method, the northwest corner method, which is very simple. So it says that to find an initial solution, the first thing you have to do is to allocate as much as possible to the cell in the upper left hand corner, subject to the supply and demand constraint. And the second one is allocate as much as possible to the next adjacent feasible cell. So we repeat step 2 until all the rim requirements have been met. And an initial solution is complete when all rim requirements are satisfied. So let's illustrate everything that we've said here. So we are going to apply it to the problem that we had. Okay. So with this problem that we want to solve, we have to look for a feasible solution, an initial feasible solution to it. Okay. So with the northwest corner method, what it says is that we come to our problem, right? So this is the initial simplex tableau. So when you come here, then what we have to do is that we locate the upper left hand cell, right? So you can see when you come here, the first one is 6. Okay, so with this 6 here, we ask ourselves, what is the maximum units that we can put here? So you can see that the supply here is 150, the demand here is 200. That means we can put 150 here. When you put 150 here, the supply is met here, so the supply constraint has been satisfied, and the demand constraint is also intact because we can put some here. So that means that since here is 150, we can't put any here. We can't put any here because it will violate this here, right? So we go to the next cell, right? So the next cell, so we need 200 here, but already we have 150 here. So the remaining that we can have here is 50. And when you add this 50 to this 150 to this 50, we are going to have 200. So it's good. So saying this one is satisfied, we move to the next cell. We need 175. We can supply 175 here, and we've supplied 50. So what is remaining? 125. But when you put all the 125 here, it will exceed the demand here. So that means that we can't put all the 125 here. But what we can put here is 100. So when you put 100 here, then here we needed to supply 175, but 50 plus 100 is what? 115. So we need to supply 25 more. So automatically the 25 will be here. So you can see that now this place is satisfied. We have supplied all the 150. Here we have supplied all the 175. Here all the demand, which is 200, has been met, and here all the demand, which is 100, has been met. So here we need a demand of 300, but we the demand of 225 has already been satisfied, and here we needed a supply of 275. We haven't supplied any, so that means we put all the 275 here. And when you put it here, you realize that this is also satisfied since we have supplied all the 275, and 25 plus 275 is 300. So this is also satisfied. So using the northwest corner method, this is how we are going to get the initial basic feasible solution. Okay, so you see we started here. When we started here, this was the first north um upper left hand cell that we're having, and the possible we could put here was 150. So we place all the 150 here, right? Then we move to the next one because we needed 200 here and we already have 150. We could just put 50 here. We went here we needed 100, and we're still left with 125 to supply. So we could all put all the 100 here and what have you. So there's the northwest corner method, which is very, very simple. Okay. Then we go to the minimum cell cost method or the least cost method, which is, I think, the simplest. So with that one, this is what we do. We allocate as much as possible to the feasible cell with the minimum transportation cost and adjust the rim requirement. So we repeat step 1 until all the rim requirements have been met. An initial solution is complete when all the rim requirements are satisfied. So with the same problem, if you are to use the least cost method to get the basic feasible solution, then we will ask ourselves that out of all the costs here, which of them is the least? And you could see that it is 4. So we will come to 4 and ask ourselves, what is the maximum we can put here? So the maximum we can put here is 200 because of the demand here. This is 275, but when you put all the 275 here, the demand here will be violated. So that means we'll put all the 200 here. Then you ask ourselves, what is the next least one? So the next least one is 5. But it is 5 because the supply here is 275. The highest that we can put here is 75. Do you get it? So that means that the supply here is satisfied and the demand here is also satisfied. So we wouldn't have to add anything here or anything like this. Alright, so then we ask ourselves, so after 5, what is the next least amount, which is 6? But we can't put anything here because of the 200 here, which has already been met. So after that, the next one is also 7, and we can't also put anything here because of this 200. Then after that, the next one is what? 8. Then with this 8, the supply here is 115, but the demand is 100, and the demand 70 has already been met. So that means the highest we can put here is 25. So that 25 plus 75 gives us 100. So the demand here is also met. So after 8, the next one is what? 10. Alright, and we can supply 150 here, but we've already supplied 25. That means that the remaining is 125, and everything will come here. Right, so here to the supply is met. So here we need 300, but only 125 has been given, and here we need to supply 175. We've supplied none, so we can bring all the 175 here so that the supply here is also met, and 125 plus 175 will give you 300, which is going to also make sure that this demand constraint is also met. So using the least cost method, then this is going to be the initial basic feasible solution. Okay, and all of them, when we do that, so for instance with this one, when we do it, we will have to calculate the cost, the transportation cost, and it will be 6 times 150 plus 7 times 50 plus 11 times 100 plus 25 times 11 plus 12 times 275. So when we compute that, we will get, let me compute that and tell you the answer. So we will get $5,925. Then when we compute the one for the least cost, you are going to get 8 times 25 plus 10 times 125 plus 11 times 175 plus 4 times 200 and plus 5 times 75, and that will give us 4,550 dollars. So now we go to the Vogel's approximation method, the VAM. So the Vogel's approximation method is also called VAM. So this method is based on the concept of penalty cost or regret. So if the decision maker incorrectly chooses from several courses of action or alternative route, a penalty may be suffered, and that decision maker may regret the decision that was made. Alright. So in a transportation model, a wrong decision is allocating to a cell that contains not the lowest cost. So we compute the penalty cost, And the penalty cost is the difference between the least and the next least cell cost in a row or column. Okay. So this is the algorithm for the Vogel's approximation method. So first, we determine the penalty cost for each row and column by subtracting the lowest cell cost in a row or column from the next lowest cell cost in the same row or column. Then the second one, we select the row or column with the highest penalty cost, breaking ties arbitrarily or choosing the lowest cost cell, and we allocate as much as possible to the feasible cell with the lowest transportation cost in a row or column with the highest penalty cost. So we repeat steps 1, 2, 3 until all the rim requirements have been satisfied. So you can read through the steps as we apply it, and as we apply it, the understanding will be better. Okay. So yes, with the same problem, we are looking at 3 different ways of getting a basic feasible solution to it, right? We've studied the northwest corner method, the least cost method, and now we are doing the VAM method, right? So we will have to first calculate penalties for each row in each column. So when it comes to the rows, right? When it comes to the first row, so what is the least cost here? 6. The next one is what? 8. What is 8 minus 6? 2. So the penalty here will be 2. When it comes here, the least is 7. The next one is 11, right? So it's 11 minus 7 is 4. When it comes here, 4, the next one is 5. 5 minus 4 is 1. That's the penalty. Then when it comes to the columns, here the least is 4. The next one is 6. So 6 minus 4 is 2. Here 5 and 8. So 8 minus 5 is 3. Here 10 and 11. 11 minus 10 is 1. So these are the penalties, right, for each column and each row. So after getting the penalties, then we take the highest. We ask ourselves which of them is the highest. So the highest is the 4, which corresponds to what? Row 2, this row, right? So we ask ourselves, in this row, which cell has the least cost? And that is this one. So here we will put the maximum that we can put here, right? You can see that the supply is 175, the demand is 200. That means we can put all the 175 here. So we put all of them here. So after doing that, this supply is satisfying, so we won't come to that row again. Then we ask ourselves, what is the next highest penalty that we have? And that is 3, which corresponds to the second column, right? And with that one too, which of the cells has the least cost? And that is this one, which has 5. And the supply is 275, the demand is 100, so we can put all the 100 here. I hope you get that. Okay. So after this, the next one is 2. So with these 2, we can choose arbitrarily. Okay, we can choose any of them. So maybe let's choose this one. So when we choose these 2 first, we can choose any of them. It works. So when we choose these 2 first, then we ask ourselves, which of them, which of the cells has, because these 2 correspond to the first column, which of the cells has the least cost? And that is 4. So we need 200. Already we have been given 175. So the maximum we can have now is 25. And this column is also satisfied. The demand here is also satisfying, so we don't come here again. Alright, so this is also satisfied. So we ask ourselves, after that we have this, right? This is 2. So here when you come here, the demand is, the supply is 150, and the demand corresponding to that is 300, right? But we can see that the lowest, the storage contain the lowest cost here is 6, but we can't put anything here because already the demand here has been satisfied. When we come here, the next one is 8, but we can't also put anything here because the demand has been satisfied. So that means everything that we have to put can be here. So that means all the 150 will be here. And now this row the supply is also satisfied in, so we don't go there, right? Then this one is also satisfied, so you can see that now this is satisfied, this is satisfied, this is also satisfied. So it's left with these two that they have to be satisfied, right? So this needs 275 and it has been given 125, so automatically the 150 will have to be here. And when you add this 150 plus this 150 to give you 300, which will satisfy this, and 25 plus 100 plus 150 is going to give you 275, which satisfy this. So based on the VAM method, this is going to be the initial feasible solution, right? And if we should find the cost to be 150 times 10 plus 7 times 175 plus 25 times 4 plus 100 times 5 and then plus 150 times 12, and that will give us $5125, right? So you can see that when we use the VAM, we had $5125 as the transportation cost. The least cost method gave us 4,550, and the northwest corner method gave us 5925. So you could see that for this method, for this particular question, so yeah, so from the three methods used, we can observe that the least cost method converges faster than the others for this example, right? So it's not a general thing, it depends on the kind of problem you are solving. So with this particular problem, the least cost method converged faster than the others. Okay, so this is the first stage. After using any of these methods, you just use one of them, right? Sometimes the question will specify which of them you are supposed to use, but if the question doesn't specify, you use any of them that you want. Okay, so after using any of these method or a specified one to find the initial basic feasible solution, then you'll have to go to the next stage. That's the second stage, to check and see if the solution is optimal or not. If it is not optimal, then you have to proceed doing some iterations until you get the optimal solution. Okay, and we will learn two methods for doing that, which is the stepping stone method and the modified distribution method, and we will solve some examples on them to really make you understand it. Okay, so see you in the next video where we talk about the stepping stone method. Then the next one as well, we talk about the modified distribution method. So see you in lesson 12.